we will start by going ahead and playing playing Gloria's video. Now, I will apologize in advance. It is my fault, not theirs, that some of these students' audio didn't come out as loud as I wanted it to. So maybe turn up your speakers while I'm playing these videos, and hopefully you'll be able to hear the students' presentations.
Okay, so in my project, I synthesized dianthyllis. Methyl dianthyllis is a component in fragrances and shampoos, and it's a two-step synthesis. So this particular synthesis was patented by Givaudan, which is a fragrance company. So originally, this was a reaction puzzle, but upon investigating the results of the IR and NMR spectrum, I realized that the IR spectrum and NMR spectrum couldn't really tell me exactly what changes were being made from each step in the synthesis. So looking at the first IR spectrum of the starting material, you can see that there's aldehyde fangs, and then comparing that to the second IR spectrum, which is the intermediate product, vanilla alcohol, you can see that the aldehyde fangs disappear. So going from the first product to the second, or the desired methyl dianthyllis, you can see that we have an OH stretch, but you can't really tell which ether functional groups are there and whether they're there. So because of that, I used NMR spectrum. Starting with the carbon-13 NMR spectrum, which didn't really show me very much. The spectrum was pretty noisy. So because of that, I decided to use a depth spectrum. Now a depth spectrum shows primary, secondary, and tertiary protonated carbons. So basically primary means one hydrogen, secondary means there would be two hydrogens, and tertiary means that there would be three hydrogen atoms on that carbon. So comparing the final product to the depth NMR spectrum, you can see two CH2 carbons, and there are two in the desired product, which means that I can confidently say that that structure was accurate for the spectrum. And looking at the photos, you can see that the first product and the second product are very different. So overall, the focus of this project was at first to elucidate the structures at each step in the synthesis. But because of the lack of evidence that was found in the IR spectrum, depth NMR spectrum, which was a new way for me to use an NMR spectrometer, was used. I'm feeling like that. Right.
Okay, awesome. So I think what it would be good, and I'm not sure, hopefully that people could hear okay. Oh, good. All right. So go ahead and I will share the PowerPoint. And Gloria, if you have anything that you want to add to what we had pre-recorded. Yeah.
So I would just like to add that while my original carbon-13 NMR spectra didn't really show me much, one way that I could have ended up using that was to increase the number of scans done on the compound, but that could have taken hours. So the depth was a quick way for me to narrow down my two ether groups that I was looking for. Yeah. Oh, also, I would like to thank Renee Sberg and my professor, Karen Goodwin, for their guidance. And yeah.
All right. Any questions for Gloria?
Yes, a question from a non-science person. Can you maybe, I don't know if you can do it in layman's speech, but can you kind of let us know what was the difference with the depth, the second tool that you used? And
So the depth spectrum compared to the photos that you see on the top, which is an IR spectrum, the depth spectrum shows it's more of narrowing you're looking more at carbon specifically rather than other things like, say, the OH. That would be shown more so by the IR spectrum, and I can see that they're there on that, so I used the depth to make sure that I had the two ether groups on the product.
Okay.
Hopefully that answers your question.
Yes, thank you.
Yes, I did enjoy exploring my own project and working with the instrumentation. It was really cool to get some more experience with it and kind of fly solo with the help of my professor. I'm not really sure what I'll do next with this. It would be really cool to look at other compounds with a depth NMR spectrum and see what other things I can look at with it. I'm not really familiar if this instrument will detect carbon-14.
Carbon. Oh, sorry. Carbon-14, if I can answer that question, carbon-14 would be invisible to nuclear magnetic resonance. It is only odd molecular weights or odd mass numbers or odd atomic numbers. And so carbon-13 is the only carbon isotope that would be available to this particular instrument. Fluorine can be looked at though with NMR. So that might be another option if you had a compound containing fluorine, but carbon-14 is not visible through this particular instrument.
This work, I think, could definitely benefit people who are looking to synthesize certain compounds and wanting to know if they've actually ended up with them at the end of their reactions. So manufacturing could definitely benefit from this. And yeah. So what am I hoping to do in my future? My major has changed a lot of times, but I've really come to enjoy chemistry. So I'm hoping to major in chemistry, and then honestly, based on the future things that I learn, I'll probably go in a specific direction. But as of right now, I just want to broaden my knowledge and see where it takes me. Do I feel IR or NMR is better for structure elucidation? I think they are both great, and in combination with each other can really give you an accurate structure for your compound. So I don't think that one is better than the other, depending on what you're looking at. So using them together is probably really beneficial to actually getting the structure that you want or that you're looking for.
So I will actually add that one of the things that I appreciated about Gloria's project was we were looking at the IR, and the proton NMR was not coming out as well. And so I really appreciated her willingness to explore something that I had never used on our machine before, and to bear with me while we worked through it. I will also point out that we had never, ever talked about depth in lecture. So it was something that was definitely brand new for her in her project because we had not dealt with it in lecture. And so I just appreciated her willingness to go out on a limb with me on that. And I was very pleased with her results. Okay, so I'm going to go ahead and introduce Gabriel Sheets. And so Gabe's project is, let me take a look and make sure that we've got it here. Yeah, it's getting ready. Okay, so Gabe's project was actually another one that kind of went out on a limb. It was using methods that we had not really discussed before and introducing chemistry, specific reactions that we hadn't even talked about in lecture yet. And so his project had a big ask. And the ask was, mix these two things together and you tell me what you get. And so Gabe really went above and beyond in looking at how to figure out what chemical compound you had created, knowing nothing about the chemistry that went into throwing these two particular reactants together. So I really appreciated Gabe's stick-to-itiveness with a fairly complicated setup, as well as some very, very unknown chemistry at the very beginning. So I'm going to go ahead and share Gabe's video, and then we will share with us some more.
Okay, my project was performed a multi-step synthesis of pyrrolidine and cyclohexanone, and the first part of this reaction was a nucleophilic addition reaction, and that created our enamine intermediate. And then going back, this reaction used a interesting glassware setup, which was simply a distillation apparatus, and that was able to, through temperature, through adjusting the temperature, you were able to reflux or distill like a few different times. And what this does is when you disrupt the distillation, that actually allows time for the reaction mixture to come to equilibrium. And so every time the reaction mixture refluxes, you're actually creating more product. And so for the second part of the reaction, that was an acylation reaction, but a special case, it's the Stork reaction, which is an acylation of an enamine. And the second part of this reaction step is a hydrolysis reaction, and that creates our diketone final product. So the whole goal for this experiment was to determine what the intermediate and final product were, because they were unknowns in this experiment. And right off the bat, I was able to tell that the enamine was our intermediate because it was a nucleophilic addition reaction. And then going into the discussion, for the first part of the reaction, I was able to see that I did in fact create my enamine intermediate, because in the starting material cyclohexanone, the C double bond O peak that was here, it disappeared for the enamine intermediate, so that was instant gratification towards that intermediate formation, in addition to CC bonds which were not shown in this picture, in this graph. And then for the second part of the reaction, we would see the C double bond O peak reappear. However, they're not shown, so they unfortunately the final product was not formed. Going to conclusions, I really enjoyed this experiment, as I felt it really boosted my, helped me understand more about distillation and reflux reactions, as well as one future work that I would do would be double the starting materials, because what I found was I got really low yield going on to the second reaction part, which disallowed me to proceed further. There was another distillation that I had to omit because I had so little yield, so I wish I would have been able to do that. And that's it.
Okay, thank you, Gabe. And so I'll go ahead and give you an opportunity if you have any additional comments you wish to make about your project. And then if we need it, I'll pull up your poster, but so far I haven't found that we've needed to refer to the posters.
So going to Dr. Jules' question, I didn't actually determine what, like a specific reason, what was lowering my yield. Yeah, I just was, yeah, so I don't really have a question. I might have to get back to you on that one. So are there any features in the IR that might determine the structure? The structure of the intermediate, or so in the IR, just that disappearance of this long CO stretch, which is really prevalent, that would show that the intermediate was formed, and then that reappearance of that CO stretch that was originally in our cyclohexanone starting material, reappearing in the final product, unknown product. Yeah, I think the only thing for the unknown product would be that CO stretch. That'd be the biggest feature that you would see in the IR.
So maybe I can clarify a little bit. Your IR product or IR spectrum of your product is not identical, obviously, to your starting material, but it's also not identical to your intermediate. So I'm just wondering if you kind of had any idea what structure you made, even though it wasn't the target molecule that you were trying to make. So do you know, is there still a carbon-carbon double bond, for example, because that's something you're trying to get rid of? You know, were there any features that were like, well, we know we still have part of the intermediate or part of the product without the carbon oxygen double bond?
Oh, yeah, I see. I know that I didn't have my intermediate, but so there's some kind of CC bond there. Also, I think I can see a sp2, so like a C double bond C bond, and on the farthest, that small peak farthest to the left, I think that's what that would be. So I have a double bond C in that final product. So I think that's be about what I think with
Kind of.
further Oh, what were you gonna
Go
say?
ahead. I was just going to say, kind of looking at it, and of course, this is only showing, his poster only has the one area of the IR showing. This actually looks very similar. Almost all the peak numbers are exactly the same. It's just the scale here this thing's a little bit broadened. So what we might be looking at here, Gabe, is a protonated amine here, like when we threw the HCl at it to try to knock it off, we might have just protonated it, and that might be why this is broadened, but that would be my best guess. I didn't ask Gabe to try to identify what he did make, because he basically had goo and only a little bit of goo at the end. So we ran the IR on the goo just to see if we could get an idea of what it was. But I was pretty pleased with what the fact that he had even come up with what he potentially had made for predicting the product in the first place. So the fact that he even knew what he was supposed to be shooting for, considering we hadn't talked about the Stork reaction yet, was pretty good. And yep, that's organic chemistry for you. What is this goo that we have?
Yeah, I definitely enjoyed exploring my project, especially working with the IR and H&MR. That always is enjoyable to me. Like analyzing, especially the IR spectrum too. I'm thinking engineering. I don't have a whole lot of exposure in that field, but I have really enjoyed the last couple of years of the chemistry classes that I've taken. So maybe chemical engineering would be in my future. I don't know.
Okay, any more questions for Gabe? Like I said, I really appreciated his stick-to-itiveness with especially with the complicated glassware he was doing. There were a lot of moving parts to that lab, and since Gabe completed it, I've actually found a much easier way to do that synthesis. That if a student wants to undertake that in the future, we won't have to do quite so many distillations, because they are kind of frustrating sometimes. They have the potential to go boom, which is what we try to avoid. And so we try to do that. Yeah, witness the glassware. It's definitely troublesome sometimes. So the more distillations we can eliminate, the better. Okay, so if everybody is ready to continue, I'll go ahead and kind of broadly introduce the next three presentations. So first, we're going to start off with Jordan Pass, who did really another use of my NMR. You might see a theme there, in that he extended the boundaries of what we had done with the NMR. I had students a few years ago all do the exact same reaction that Jordan did. And then we had to analyze it by taking it up to St. Martin's. They opened up their organic chemistry lab for me so that my students could go up there to analyze the products and figure out some actual ratios. And so when I got my very own NMR, I was really hoping that it could be used for this particular experiment. It's definitely not as precise, or doesn't have quite the parameters that, of course, the ones at the universities did, and it worked beautifully. And again, thank you to Jordan for, letting me use him and his project as a guinea pig to check the capabilities of this. So I think I'll go ahead and let Jordan go, and then I'll introduce Ashley and Ben separately. So I will go ahead and share, and here we go.
All right. I did my research project on the isomerization after the oxidation and reduction of borneol. So I took borneol, which is also used in like fragrance, food flavoring, that kind of thing, just to give it a nice fragrance and a nicer taste if it's more on the minty side. So the first step was the oxidation, which I used pool chlorine. And the main point of this was to turn it into camphor. And if you go over to that. Yeah, so it took the ketone right there, and it has it'll turn itself into two isomers, which means depending on where the nucleophile comes into attack, it's either can attack exo or endo. And the whole point of this project is that I was figuring out the percentage in which it turned into that isomer, what it tended to do. So walking through the mechanism again, we're going to go get the oxidation in the first step. It's going to turn into the product camphor, which is kind of like a mid product, I would say, an intermediate product. Then we're going to do, I did a reduction using NaBH4, which then turns it back into borneol, but also present is its isomer isoborneol. All right, so to determine these percentages, I used Nmr and Ir. Starting with the IR, see we have three images right here. The starting product, you can see at the top, that is a presence of the OH group that we saw in the starting product right there. In the middle, in camphor, you see that the oxidation was successful. There's absence of that OH group. And then in the final IR for both the mix of the isomers, you can see that the OH group is back present. So that means, that indicates, at least I've made the final product, that's successful. And then to determine the percentages, I integrated the NMR spectra. And here was the starting product of borneol integrated was a 80-20 mix percentage-wise. So it would be 80% borneol with 20% isoborneol respectively. And at the final NMR for the final product, you can see here the borneol is significantly reduced, and there's a larger presence of isoborneol integrated. This was integrated to a 90-10 or 9-to-1 ratio for isoborneol, which would mean, going back to the mechanism, that the endo attack tended to be the more common one, and isoborneol will be your majority of your product at the end. Future work for this project, I didn't get time to go into it, but it would be to run the final product through gas chromatography, and that will give you a much more accurate percentage of the isomers rather than going through and just integrating through the NMR.
Okay. Jordan, anything that you would like to add to that? I'll get your poster ready in case anybody wants to look at it.
Yeah, there are a couple things. One, I'm glad I didn't and ah as much as I thought I did. So that's nice. One of the things, it would be interesting because I didn't catch it until later, is I would be interested to see if it was the same ratio coming out, if it was just 100% borneol as the starting product. Just out of curiosity, if that would make a difference. And just for the sake of specificity, to run it through the GC at the right parameters, just so I could get a more accurate idea of the percentage of the isomerization. That's kind of not been super bugging me, but it's just one thing that I wish that I had time for.
Right. One of the things I will point out to the audience on your project, so when we ran that first NMR that was from the bottle marked Borneol, and we saw the hydrogens for both Borneol and isoborneol, and we were very confused. And I thought, well, that's not right. Something's not right here. And we picked up the bottle and moved it a little closer and read the fine print, and it said 20% isoborneol. So it was actually a neat discovery because it allowed us to know what a ratio was and not have pure at the beginning, and then be able to actually use that data to figure out the percent of isomerization and to actually see that it had completely flipped.
Yeah.
So that was fun to know, to read the bottle.
Yeah, I feel like that should have came to me a lot earlier, but
Well, why would it? The bottle said Borneol.
and to caveat off the introduction, because I did run these things on the NMR initially with only, I don't remember the right wording, but essentially only one run, like one scan. And the NMRs were coming out like a very noisy, very fuzzy, like it wasn't very well defined. So we actually had to go in and adjust it. And we actually ended up going to 20 scans so that it narrowed it down. And I mean, it took, exponentially more time, but it got great results. And I was really impressed at the integration was right at, like, the starting product was exactly 80-20. It's yeah, I was really impressed. And even the IRs came out great. I thought it was nice. Not to toot my own horn, but
It did well. So you got a couple of questions. Are you able to see the chat?
I do.
Okay.
Gloria, I chose this because it interested me actually back when we were all taking biology with Dr. Norton together. We talked about isomers in food, where they interchange glucose and fructose in the, like, those isomers, just so that it binds and it tastes better. It tastes better to us. So they manipulate isomers like that, which I think, so that's why I chose it, because it reminded me of that. I thought that was really, really cool. This is kind of important. I just thought it would be very interesting. Michelle, I'm doing pre-med, and then I want to go to med school eventually, once I get the prerequisites to take the MCAT, and then not sure what specialty, but I want to be some type of a surgeon, probably like orthopedic or maybe cardiothoracic. Yeah, and Dr. Norton says right there, there's a lot of different things, that the importance of knowing what you're getting and how much of it you're going to get every single time. So Dr. Norton had brought up the drug. So yeah, it's going to be huge in any pharmaceutical aspect, food. I mean, I don't think you could sit here and list all of them. Yeah, and thank you, Professor Goodwin. I appreciate all your help through it. Renee, thank you, and thank you everyone be here to listen to me. Appreciate it.
Great. So I will follow up with one more comment before I introduce Ashley, and that is that the year that I had all the students do the same project, one of them walked into just working out at the gym and noticed a fellow gym member was wearing a shirt that said, "I heart NABH4." And she went up to him and said, "I'm working with sodium borohydride. Why do you love it?" And he said, "Because it makes me money. How are you working at it?" And so she started talking to this person, and she came back the next week to campus, and she came up to me and she said, "Professor Goodwin, I networked and it got me a job." And so that student, actually, whose name was also Jordan, female Jordan, is now actually working in the chemical industry, all based on an experience and, again, taking your knowledge out into the world and networking, which is something that we all can learn to use. Exactly. So I'm gonna next introduce Ashley. And so Ashley has actually been kind of one of my personal inspirations. Ashley, I don't want to make you cry before you get started. Ashley came to us from a business major, I believe, and she took was it 121 that you took?
It was with Emily Sprafka.
Exactly. So she got inspired to change her entire major, change her entire degree, and is now actually a pure chemistry major on her way to PLU with a very nice little scholarship to PLU as well. So Ashley decided pretty early on that she wanted to work with me as a research student, and because of her interest in pharmaceutical development, I wanted her to get a taste of what is called combinatorial chemistry. So her project today is actually the culmination of an entire year worth of researching and looking at combinatorial chemistry. So I'll go ahead and play your video, Ashley, and then you can answer questions and talk more about your project.
Sounds good. Thank you.
Okay. All right, guys. So my project is based on combinatorial chemistry. As you can see in the title, I was just exploring the main concepts of what it is. And so the pharmaceutical industry adopted this principle, but before this, before they would find it and research a drug and create this drug, they would have to go through so many compounds and test each one individually, but also synthesize each one individually. And you can imagine how long that would take, especially in times when drugs are in high demand. So what combinatorial chemistry is you could create a vast number of related but diverse compounds in mixtures, also known as libraries. And so in this, they could also, in mixtures, they could test them at the same time. So imagine that would take up, that would be so efficient, and it would just save so much time and money, right? So this project consisted of 3 different parts. So I created azo dyes, I synthesized esters, and I also synthesized an antibiotic compound. So for the first one, I synthesized 9 azo dyes. And here, if you could see in figure 1, I synthesized 2 of them. I'm just showing you 2 of them. And the azo dye project mainly emphasized and illustrated the concept of diversity in structure-function relationship. So these are one of the 2 compounds that I used in each one of these, so from left to right. And the other one was a partnering compound that didn't change, so it was the same compound. So this is the only thing that changed. If you could see, they have the same groups connected to the ring. The only thing that changed is the structure, so the placement of these groups, right? And with the difference in placement, you got a whole different color, which is so cool. So that really illustrates how changing the structure gives you a whole different compound. And that makes it so much easier. And so for the Ester Lab, I synthesized esters. And if you know what esters are, they're usually found in nature. So like bananas, pears, apples. And my target was wintergreen. And so you could see that I synthesized it right here. This is just one of the reactions. And so I synthesized maybe 12 esters. And so using the same reaction. So it was between a carboxylic acid and an alcohol. And I just made a bunch of esters until I found which one was wintergreen. And so this one really illustrated how I could create a bunch of compounds using just one reaction. And then so for the third part, I synthesized an antibiotic compound. So what I did first was, with the help of Dr. Joel and Eli, I inoculated some plates with E. coli. And so that was for the biological assay part. So, but first, I created mixtures. So this is where the mixtures comes in. And so I created mixtures of compounds, and I ended up with 6 mixtures. But I started with 9 individual compounds. So if we synthesized each of the 9 individual compounds and then tested one each individually, that would take so long. But if for this one, I only did it in 6. So compare 9 to 6, that saves a lot of time. And then imagine from like 100 to like 10. So in here, I synthesized them in mixtures, and then after I tested them as well in mixtures on the E. coli plates to see if any of them had antibiotic activity. And so if you could see in figure 4, mixtures 2 and 6 showed positive results. So one of the compounds, there's 3 compounds in each one. So one of the compounds in each of those was tested to be an antibiotic compound. So to figure out which one, we had to do a deconvolution table. So these are all the possible compounds that we had, right? And so each one, these are the mixtures, and these consisted of each of those compounds. And so right where the 2 intersect, the ones that showed positive results, that's where you could see which one was the positive, which one had antibiotic activity. All right. And so this one really illustrates how we could simultaneously synthesize but also test them at the same time. So instead of also testing these ones over here that showed negative results, we saved so much time just focusing on the ones that showed positive results. So overall, the purpose was to just explore what combinatorial chemistry is and how helpful it could be to the pharmaceutical industry. That's it. I think I would do that again. I'm sweating.
Sorry, I tried to get it off before that. Oh, Ashley. All right. We were all sweaty that day.
That was hilarious. Okay. Thanks for the introduction, Karen.
You're welcome.
That was good.
Go ahead. Anything you'd like to add?
Yeah, I want to go into a little bit more detail. For the azo dyes, I dyed them on multi-fiber strips. So they did have some synthetic materials as well as some natural, like cotton, worsted wool, silk, and some others. I was supposed to meet up with Liz Fry, but I didn't get around to it because I just had so many other obligations and time didn't allow. But so for future work for that, because I didn't really have any other future work for this project, because mostly it was just for me to get just a general idea of what combinatorial chemistry is and why the pharmaceutical industry uses it. But I would love to know why the dyes didn't, if you see it in figure, I believe 1, pull it up. Thank you. Some of the materials didn't absorb the dye as well. And I feel, just tell me if I'm wrong, but I think it's because of the polarity of the bonds and that's why it didn't hold on to the material as well. And for the Ester Lab, so esters are usually found in nature. And so like in lab, we synthesize banana oil. But for this one, I had to figure out which one was wintergreen. I had 6 carboxylic acids and 6 alcohols. And so in theory, I could have made 6 esters, but I made around 12. But then once I found wintergreen, the way I knew that it was wintergreen was I characterized it by just smelling it, but I also made sure it was wintergreen and made sure that it was an ester by also using the IR instrument, just as my other classmates did. And that's pretty much it. Are there any questions? Oh wait, just kidding. Okay, for Dr. Norton's question, yes, so the chemical mixtures, I was able to test them all together, and the main purpose of combinatorial chemistry is for efficiency. So instead of doing 9 mixtures or 9 individual tests and reactions, I was able to do it in 6. But there is some consequences to that and some cons, because there could be side reactions between the compounds in the mixture. So we do have to be careful with that. And yeah, so it's not all pros. I really want to go into pharmaceutical research. So that's my end goal. And so that's why Karen Goodwin introduced me to this project and had me work with her. And also just want to thank Dr. Jewel, Eli Perez, Renee, and Karen for being patient with me and helping me with this project. And the foundation for funding, of course. Thank you.
Very good. Bailey would like to know what inspired you on this capstone. Did you have any like aha or big picture moments? Sometimes I choose projects for students based on their interests, and then they get going on them and they're not having as good a time as I am. So I usually let them quit. And you just kept like every day that you came in, you were happy to be there. And so I would also like to know what inspired, what inspirations did you have from this project?
So before or after I changed my major to chemistry, I was really interested in the pharmaceutical field because I realized how much I love being in the lab. And then going into the drug industry, I just really want to help people. I feel like with pharmaceutical drugs and all this, I strongly believe that the holistic approach is best, but then when that doesn't work out, I think it's so amazing that we have pharmaceutical compounds that we could use to help people, especially in times of when these drugs are in high demand. So it's mostly, I just really want to help our community, and yeah.
So the last question by Dr. Jewell, are any projects coming out of the libraries for the future between DIES and the art department, for example? I'll actually field that because it actually gives me a little way to plug next winter's course. So talking to Liz Fry about this, her main interest for dyes are actually naturally occurring organics and not synthetic organics, which these were synthetic organic dyes. However, in winter quarter of next year, I am actually designing a non-majors chemistry class, chemistry in art. And one of the labs is actually looking at a variety of both synthetic and naturally occurring pigments to create paints from. And really shameless plug, thank you, Ben. And so that's what Capstone is. So Ashley actually really inspired me to start thinking about that course when she started this project in the fall. Like, there is so much chemistry and art combination, and that would just be a perfect way for our non-majors who you know, are more humanities talented to be able to knock off natural science credit, also playing into their own wheelhouses and being inspired by art, and then finding out the chemistry from that art. So yeah, it's going to be amazing. So I'm going to next introduce Ben Corwin, who is another student that is heading off to university with a nice scholarship. He's heading to St. Martin's in the fall. And so his project came about. He is actually, his and Ashley's, what I've done since the beginning in Capstone was I used to let students just choose anything they wanted to do from the literature. Have at it, guys. And what happened one quarter, I had about 6 students, and every one of them was doing a project that I had no idea anything about it. And it kind of got a little dangerous that quarter. I thank Renee for sticking with me for that quarter. And after that quarter, we wiped the sweat off of our brows and said, you know what, I think we ought to limit the presentations to things that we can control. However, when it got time for the projects for this year, Ben came to me and asked if he could perhaps look at a project that was more in line with his future interests, and that is in forensics. And so we dug around a little bit in some literature and found a really neat forensic themed lab project for him to do. And not only did he replicate what was done in the literature, which is a lot of what my students' project are, is more of a replication than a pure research. He actually took it in another direction again, and thank you for being patient with me as I wanted to kind of expand your horizons and allow you to see some other techniques that we hadn't talked about in the chemistry course. So I'm going to share Ben's video, and then we'll hear from Ben.
Okay, awesome. So for my presentation, it was a forensics themed lab for non-science majors. Basically what we had is we were given a situation, and the situation was that there had been a body found in a lake, and we were supposed to determine whether foul play was involved. And the one way that we know how to do this is through chemistry. So we used organic techniques in order to determine if foul play was involved. One of the first things that we did is we looked at 3 of the samples that we were given. So we were given a water sample from the lake, a water sample from the lungs because it was a drowning victim, and then we were given a shirt sample. So we wanted to test what compounds was in the lake, the water, and on the shirt. And we did that through infrared spectrometry. From our graphs here, so we have figure 1, 2, and 3. This first one here, the first 2 are going to be of the lake and of the shirt. And you're going to see that we have organic compounds that are present. And the main thing to observe from this is that we have the peaks that are showing compounds present. And then if you look at figure 3 here, you'll see that there's not really anything present there. And this is showing us that there's a difference from the lake water to the lung water, which implies that there are different sets of water, possibly a body was moved. So in figure 3, we don't really have much there, so we're thinking something purified, some purified source, possibly pool water. One way for us to test for that is to look for the chlorine that is often found in pool water, and we do that from a silver nitrate test. So in this figure here with the 2 beakers, there's the clear samples. So we have the one on the left, which is the lung water, and the one on the right, which is the lake water. They're both clear without anything in it, but once we add the silver nitrate, you'll see that the one on the left, the lung water, turns all cloudy, which shows that there was chlorine present in the water. So from this data here on the water, we know that there was there were no compounds really in the lake water that showed up in the lung water, and that we had chlorine, which is implying that we had a filtered pool water or some kind of filtered water that had chlorine in it, which shows us that the body was not drowned in the same body of water that it was found, which does indicate foul play. And then going further, we were given another sample, and this sample was of blood. And we were told that we had GHB in the blood, which is a date rape drug. This drug is prescribed, though, sometimes. So the problem is that it's a drug that can be prescribed, but also it is used in parties, and it's given to people drug people, and then they get raped. What we needed to test for is that it wasn't something that was taken that was prescribed or that had come in contact with, but that the concentrations were high enough to show that someone had been actually dosed with it. And one way to quantify our blood sample is through gas chromatography. And so we use the method of standard additions, where we basically just take the standard sample and we add some more to it. We get a graph, and from the graph we're able to extrapolate backwards down to the x-axis and find the concentration. And this concentration, it just basically was able to tell us that this was a very high concentration, higher than what someone would be prescribed, actually enough to possibly be a lethal dose. But the main thing from this is that it's showing that it wasn't something that they came in contact with, and it wasn't there by chance. It was given to them, and it was another indicator that there was some kind of foul play involved, and it's another thing that can be presented if this were to be presented in a court of law. So we would have that the body was moved and that there were drugs involved. So the whole goal of this experiment to determine if foul play was involved, it was proven that foul play was involved, and now from this, it allows students to be able to take their data and they can write a report on it. And the goal was achieved, and overall it was successful, and it was done in a way that they can learn about the chemistry behind it while still being able to apply it to a real world situation.
Okay, awesome. Ben, do you have anything to add to that? Before we jump into questions.
There we go. So yeah, well, I have a few questions that I see there. My questions aren't showing up super well. Okay, was the question, would we be able to tell if there was salt, if it was a salt water pool? Okay, awesome. So yeah, the way that the tests work is that, you know, the chlorine is going to ionize. So we're able to test for, we use a method called Volhard's method, and we're able to test for chlorine that way. What is it? Sodium hypochlorite that you find in like bleach and chlorine, we can also test for that using a few different titrations, but this was specifically looking for the chlorine ion. And we use Volhard's method for that. And some people did state that there can be amounts of chlorine that are found in lakes and such, but Volhard's method, you can use titration and find a concentration, and you can discover that it is a high concentration, and that it's also, we also had purified water, which showed that that it wasn't lake water. Did I run any local water samples from China Creek? I did not. That would be a good idea to run that. But the situation that we were given is that we had lake water. The goal of this was not necessarily to examine for specific compounds via like our IR. Our IR was just to determine if there was differences, which was determined. Running local bodies of water would be helpful if we were looking for which body of water they were drowned in. But since it was purified and had such high concentrations, it would be unlikely that it would be another natural source of water. We were looking for an artificial or a purified and manufactured source, not something that's necessarily from a creek. So would we classify it as a homicide? That's a good question. Honestly, I don't have enough information to classify this as a homicide. The goal of this was to determine if there was foul play and if the person drowned from natural causes. The person did not drown from natural causes. They did not, well, we don't know if they drowned from natural causes. They did not drown in the lake of water that the body of water that they were found in. It just shows that the body was moved, which leads to other investigation to be followed out. I can't determine though if that person fell in, hit their head, anything like that. We weren't given any of that information. As a forensic scientist, I wouldn't be given that. I was just there to determine if the body was moved, and that's what we did.
Ben, you're making Emily and I both so proud right now.
Oh, thank you.
He's throwing some hard questions your way, man. That's awesome.
Thank you.
So I would like for Ben to have a couple more questions, but I also want to, I don't know whether I should probably ask him privately in the chat if you would like to share what you are currently trying to do.
So yeah, I was just late to the meeting. I just had a polygraph with Washington State Patrol. I'm currently applying for an internship with the Washington State Patrol Forensics Bureau. I passed my polygraph, and so I'm moving on to the next stages. And yeah, they're just finishing up some background investigation. I'll be working mostly with latent fingerprints, but my goal in my career is to do more toxicology. I'm just trying to explore more in forensic science right now, though, just get my foot in the door. But right now, for the next little while, I'll probably be doing some latent prints. Hopefully toxicology soon though.
That's just even when Ben and I were working on this and he mentioned the toxicology part was not a part of the original literature. And so it took me remembering back to the frightening amount of quantitative analysis I had to take and digging out some old books, and then Ben being very patient with me and vice versa. and a couple of heated discussions as we were both trying to talk our way through this. And I really appreciate Ben. I told him that he challenged me in a respectful way, and his comment was that it always wasn't respectful. And I beg to differ. It was always respectful, but you know, we do need to be able to challenge one another. That's what science is as well. And so I hope that I give all my students that kind of ability to be able to question what you're hearing if it doesn't sound quite right. Just not in the middle of lecture, especially over Zoom. All right.
Yeah, and I would real quick just like to thank Professor Goodwin for giving me the opportunity. She does really set up a great collaboration, and it helps for us to solidify those ideas so we have a better learning experience. So I'd just really like to thank Professor Goodwin. Also, big thanks to Renee for helping keep us all safe in the lab and for setting up a lot of our experiments.